Hello and welcome to chapter 15. We're going to talk a lot about chemical equilibrium in this chapter. We've presented this concept before, but now we're going to really dive into what an equilibrium means and how does that reactivity affect our kinetics, affect our thermodynamics, affect our overall reaction chemistry. One really good real-life example that we have is hemoglobin. Hemoglobin is a protein found in our red blood cells, and it reacts with oxygen. Now, we breathe in oxygen, and hemoglobin is the transporter that carries that oxygen around our bodies. So when we think about what hemoglobin does is it attaches oxygen so that we inhale it and take it into our bloodstream, but it also needs to let it go once it gets to its location that we need the oxygen to be at. So when we look at this reaction, one thing that we definitely notice here is that the reaction arrow itself is quite different from what we used to see. Instead of just a forward arrow, we see these reverse arrows as well. It's an equilibrium arrow. That arrow, where we have a half forward, half back, describes the process of an equilibrium. We call it a dynamic equilibrium. Now, what this reaction tells us is that hemoglobin and oxygen can come together as reactants to form a combined molecule, which we see on the right-hand side, the product side, HBO2. It's a connected hemoglobin-oxygen bond. But that product can also separate and go backwards to form hemoglobin protein by itself and oxygen gas by itself. And that process is very important for our body in order to function. Now, the concentrations of all of the reactants and products in that equilibrium reaction are all interdependent. The relative amounts of hemoglobin, oxygen, and HBO2 at equilibrium are related to a constant called K, the equilibrium constant. Now, a large value of K equals a high concentration of products at equilibrium. That would mean that products were favored. If we had a low equilibrium constant K, a small value, that would indicate that there is a high concentration of reactants at equilibrium. What we're going to see as we dive in is K is going to be equal to the concentration of the products divided by the concentration of the reactants. This will be true no matter what equilibrium reaction we are talking about. And the changing concentrations of any one of these, hemoglobin, oxygen, or the product, HBO2, necessitates changes in the other concentrations to restore equilibrium. At the very end of this chapter, we will talk about Le Chatelier's principle, which tells us how equilibrium can be affected based off of different concentrations. But let's just take a look. In the lungs, the concentration of oxygen gas is very, very high. Take a moment, breathe in, take a deep, deep breath. When we breathe in, we increase that amount of oxygen. And by doing so, it shifts the reaction to the right to produce more product, binding oxygen with hemoglobin. In the muscles, once hemoglobin leaves the lungs with its oxygen bound, it goes into our bloodstream and it gets to the muscles. And the concentration of oxygen is very, very low. The equilibrium then shifts because we're missing some oxygen to the equilibrium. So that decrease in concentration requires us to imagine that the hemoglobin oxygen breaks down, it dissociates to release the oxygen in the muscles. And it all has to do with the amount of concentration of one or many of our reactants or products. Now, when we talk about the reaction dynamics, when a reaction starts, the reactants, of course, are consumed to make products. At the start of a reaction, we are going to assume here that we only have reactants, right? and the reactant's concentration starts to decrease and the product concentration starts to increase. And as they do that, we've already discussed a lot of rates of reactions. As the reactant concentration decreases, the forward rate of the reaction decreases. Remember, our rate law is dependent on the concentration of reactants. And so as that reactant concentration decreases, the rate decreases. Now, for a dynamic equilibrium, eventually the products can react to reform, go backwards, reform those reactants, assuming that the products are not allowed to escape. We'll talk about that, what that means. But if we are in a closed system, let's imagine that we have A going to B. The forward rate of the reaction, A going to make product B, would be this rate law. But we know as A decreases, the rate of that forward reaction is going to decrease. For a reversible reaction, there is also a rate. I'm going to call it K to the -1. The reverse reaction is going to start ramping up. As we make more product, the concentration of product increases, the reverse rate of that reaction is going to also increase. So processes that proceed both forward and reverse are said to be reversible, and a dynamic equilibrium is established when these rates of the forward and the rate of the reverse reaction are equal as well. So chemists commonly use two different kinds of arrows to indicate a reaction completion. All right, the single arrow is what we've been utilizing thus far. That's a yield sign. Single arrow, it means that the reactants are converted to products. A double arrow indicates that the reaction is in an equilibrium, that it is reversible, that not only can we imagine the reactants making products, but we can also imagine the products making reactants. A dynamic equilibrium is a condition wherein the rates of the forward and the reverse are equal. Because the forward reaction slows and the reverse reaction accelerates, eventually they will reach the exact same rate. Notice here at this dotted line, we have a bunch of reactants and products. This would be the reaction of H2 plus I2 going to make HI. It is a reversible reaction. So once we start making HI product, there will be a point in time when we start to see an establishment of a constant concentration. Same thing with the reactants. We'll start to decrease the concentration and eventually we will reach a constant. No matter if it is one reactant or two reactants or a product or two products, all the concentrations will really start to become constant. Now, once that reaction reaches an equilibrium, the concentrations of all the chemicals remain constant because the chemicals are being consumed and made at the same exact rate. The dynamic equilibrium is established only when the rate of the forward is equal to the reverse rate. All right. Now, equilibrium does not mean equal amount of products and reactants. The rates are equal. The rate of production of product is equal to the rate of production of reactants, but that does not mean that the concentrations are equal. It just means that we have established constant concentrations. They won't change any more than they already did. Now, some reactions we reach an equilibrium only after almost all of the reactants are consumed. And so we'll say that those reactions, the equilibrium favors products. There are some reactions that reach an equilibrium when only a small amount of products have been made. And so we say that those reactions, the equilibrium favors the reactants. So we do not establish any concentration identity to those reactants and products at equilibrium, except that they are constant. They reach a specific concentration based off of the dynamic equilibrium set by the reagents themselves. Now, how can we calculate anything in this area is by looking at the equilibrium constant K. The relationship between the chemical equation and the concentration of the reactants and products is called the law of mass action. It's how we determine anything about establishing equilibrium in a reaction. Now, with this law of mass action, the balanced chemical equation, that overall balanced equation, will be able to determine our the way we calculate K. Notice that it is products, C and D for this generic reaction down here, divided by reactants, just like we talked about earlier. Now, what's useful about the law of mass action is that we actually can use the coefficients of the balanced chemical equation as exponents. All right, the lowercase letters in front of A, B, C, and D, those are the coefficients, and they will always be able to be the exponents in the law of mass action. K is the equilibrium constant. The only unique thing about K is that it does not have units. We assume no units, even though we are using concentration, molarity, and we'll also see that we can use partial pressures for gas reactions, but the overall units of K will not be anything. They'll be unitless. So let's just practice. Here's a reaction. We know it's at equilibrium because we see the equilibrium arrows. So we can write the K, remember it's products over reactants. One product I see is NO2. It's got the coefficient of 4 in front of it, so we put that NO2 concentration to the 4th power. We multiply it by any other product. Oxygen. Oxygen has a coefficient of 1 in front of it, so the exponent would be 1. All right, divided by reactants. N2O5 to the 2nd power. There's our equilibrium constant, K. Now, what does the value of K mean? When K is greater than 1, think about products over reactants. If that is a large number, that means that we have more product molecules present than reactant molecules. So we would call that reaction product favored. Means we make more products than we do reactants. We still may have some products and reactants existing and reacting, but there's definitely more products than reactants. This would be something like 10 to the positive 7, 10 to the positive 20, right? When we're looking at K values, the K for this specific reaction at a given temperature is usually around 1.9 times 10 to the 19. Again, unitless value, very large number, products favored. What does the value of K imply if it's less than 1? When we have a value of K that's less than 1, the reaction reaches an equilibrium and there will be a lot more reactant molecules. Again, if this is a very small number, the denominator or the reactants are in larger quantities. So we always would say that the reaction is favoring the reactants or reactant favored. Now, when we see something like this reaction, N2 and O2 combine to make 2 NO gas particles, a typical K, 4.1 times 10 to the negative 31. That negative exponent for above 10 tells us it's a very, very small number. And so that would be when the reactants are favored. The relationships between K and our equations Again, when we think about manipulating a reaction, just like we've done with Hess's law, when the reaction is manipulated, the K is also manipulated. So an equilibrium constant for a forward reaction is what we decided, right? Products over reactants, using the exponent for our coefficient for our exponent in that balanced chemical equation. If we wanted to reverse the reaction, flip it, right? Draw the K of the reverse reaction. Again, products over reactants, and how that chemical equation is drawn tells us A times B over C times D. And so when we look at what happened, K of the forward is equal to 1 over K for the reverse. So we flip a reaction, products become reactants, reactants become products. How we write them, we invert the K value. When the coefficients are multiplied by a specific factor, say we want to multiply everything by 2, right? Multiply this by 2, and we get a new reaction. What would we do? Well, let's imagine where does that coefficient go? It goes in the exponent. So for this new K value, we'll call it K2. Products, 2 times C. 2 times A. 2 times B. So really what we've done here is we've taken the normal K1 and we've squared it. So whatever coefficient you multiply by, that's what you would put in the exponent. K1 is equal to K2 to a specific power, whatever power you multiply your reaction by. Last one that we're wanting to think about is when you add new equations. This is our last thing that we did with Hess's law, so this is the last thing we need to bring back up again. When you add multiple equilibriums together, let's just say A goes to B and then B goes to C. If we wanted to add those up, just like before with Hess's law, I'm going to write them out on top of one another so we can see that same format we've done in class. Right? We would add these up to get A yields C. And this is our new desired K value. Well, let's think about it. For the reaction that we see, products over reactants, we'll call this K3, the new K value for that third equation. What we've really done is we've multiplied K1 by K2, right? The B's cancel each other out. And what we're left with is C over A. So K3, when you add two reactions together, you multiply their K values. When we have reactions involving gases, we can still do the exact same analysis that we just did with concentrations of a gas mixture. We can also use partial pressures as well. So there are two ways that we actually can write a K value. Kc would be using concentrations, molarity, products over reactants. If we have a reaction like this one, where we have gas phases, we can also use the Kp, measuring the concentration of each individual component by the partial pressures. Still, the partial pressures would be to the exponent of whatever coefficient. And the partial pressures will still be products over reactants. Now, concentration and pressures are very different. They are definitely different units. So in calculating the Kp, the partial pressures are always in atm. When calculating a Kc, the concentrations are in molarity. The values of Kp and Kc are not necessarily the same because of these different units that we derived them from. The only time Kp and Kc will be the exact same is when there is no change in the overall moles of the reaction. The relationship between them, if the moles do change, is this equation. Kp is equal to Kc times RT. Yes, that's the gas law constant. R equals 0.0821 liters atmospheres over moles Kelvin. T is temperature in Kelvin, and delta N, the exponent delta N, is the change in moles. Delta N is final moles or product moles. Add up the coefficients of the products minus the initial moles. Add up the coefficients of the reactants. Excellent.